Thank you for joining me and welcome to this talk on adversarial attacks on LLMs. So I'll go ahead and share a link to the slides and you can follow along. So with that, I'll give a brief introduction of myself. So I am a software engineer with experience in an intersection of high performance backend systems, data, and machine learning. I have great interest in improving accessibility and building more inclusive technology, which improves experiences for people with disabilities. I also dabble in other things in the tech space, including writing technical blogs and contributing to open source. With that brief introduction of me, let's move to our main agenda. So in this talk, I'll focus on four main areas. So we will talk about what adversarial attacks are, see some examples to get a better understanding. Then we will explore how they're done and why we should be concerned about them. And finally, we will cover defenses that you can use to protect your model. So let's go ahead and define adversarial attacks. So an adversarial attack is an attack on a neural network where a subtle, carefully designed perturbation to the input leads to an incorrect prediction while the original input is still classified correctly. That is if you're using like if our neural network is a classifier. But this is applicable to other neural networks. So that is the perturbed input will produce an incorrect output while the original input still gives a correct output. So although the change may be invisible to the human eye, the change that we introduce to the perturbed input, the model considers this change significant enough to change its prediction. So the concept of adversarial attacks is not new, and we can say this from as far back as 2004, where researchers showed how traditional machine learning models could be fooled. And in 2013, 2014, the topic gained momentum as more researchers showed how deep learning models were also vulnerable to adversarial attacks. So since then, there have been great advances in the area where researchers have demonstrated different types of adversarial examples and how they fool models. So let us first go through an example of an adversarial attack in computer vision for simplicity so that we can move to an example in the LLM space. So for this, here in this example, the classifier can classify the input image as a cat with high confidence, and it would be indeed correct. Then when we add some noise to the input image, the classifier predicts that the image is a dog. This could be a bit puzzling and funny because we can clearly see it's a cat, and the noise introduced does not make us think that the image is anything else other than a cat. I think even the second image still looks like a cat, even if the model would classify it as a dog. So the perturbed input, which is classified as a dog, is referred to as an adversarial example. So you may be asking yourself, why did the model change its prediction? So the perturbations we introduce, that is the adversarial perturbations, are carefully designed to trick the model into making a different prediction. So let us explore an example in the natural language processing space, which is the focus of this talk. So we will use two examples. So in the first example, we see that we are using this is a sentiment analysis model, and the classification model was fooled into misclassifying sentiments by just changing one word in the sentence. So the original sentence is perfect performance by an actor, and that it gives a correct prediction that this is a positive sentiment. Then in the adversarial example, we change perfect, the word perfect to spotless, and so the second sentence is spotless performance by the actor, and the model for some reason predicts this as a negative sentiment with 100% confidence in this prediction. So semantically, we can see that this sentence has not changed and communicates the same idea, but the model takes that word, like that one word makes a big difference to the model and makes it change its prediction. Then in the second example, here we have the sentences appear to be the same, but like the model. So for example, in the first sentence, we have send money to the account 1234, and then this is what a human sees, and then in the model, the input that will be subbed to the model will be send money to the account u plus 2, that sequence of numbers, which is actually imperceptible to a human. So there is imperceptible noise added to the sentence, and this causes the model to change its output. Here the task is to translate from English to French. And so this attack is quite clever in that the characters added to the input cannot be perceived by a human. So basically, if you saw this sentence as an input to your model, you would not suspect it as being an adversarial example, or even as an attack to your model. You'd probably just process it only to realize it was an adversarial example. Yeah, then having seen these examples, you might be wondering, how do attackers achieve this, and how are they able to determine which word or which imperceptible character would trick a model? So yeah, let's explore that in the next part of this talk. So adversarial attacks on neural networks can be done through different approaches. So in this talk, I'll focus on gradient-based attacks, and gradient-based attacks are white box models. So let's back up a little and yeah, so what are white box attacks? So in a white box attack, the attacker knows the model architecture, the model's parameters, and the training dataset. So with this knowledge, they can design an effective adversarial attack. And for these kinds of attacks are easy, especially on open source models where this information is easily available. And so someone can rely on the gradient to find a way to make those changes to the input. Then, as you guessed, of course, there are also black box attacks, and here is where the attacker does not know the model's architecture and relies on the output to design an attack. So this would be a closed source model where you only receive, maybe you send an input. For example, if it's a sentiment classifier, you send some sentiment or write a prompt, and then whatever you get back, based on those outputs, you will design your attack based on those outputs, but you don't have you don't know the model architecture, and you also don't know the weights, you don't know the gradients. That kind of information is not available to you. Yeah, then let's move to how how adversarial attacks are generated. So gradient-based attacks are based on the idea that we rely on gradient descent during training. So while training a neural network, we're usually trying to reduce the loss function by updating the weight. Basically, we're trying to find what change in the weight decreases the loss function. So here we're trying to, like after we've done the initial weights you've introduced to the model, you try to find whether the loss, how you can decrease the loss function by changing the weight. So on the other hand, in an adversarial attack, what you're trying to do is to determine how a small change in the input can increase the loss function. So the attacker tries to perform a gradient-guided search over the tokens and generates trigger sequences, which when appended to the input will generate an incorrect output, making that way they are able to fool the model. So for instance, in the previous example, we've seen that the triggers are those imperceptible characters. Those would be the trigger sequences that the attacker was able to find through gradient descent and through simply searching over basically following a gradient guided search over what tokens would help increase the loss function. Then, so the next thing you'd be wondering, okay, so we've talked about what adversarial attacks are, we've talked about how they are done, and the other thing would be, okay, I know all about this, why should I care about this, or why should we be concerned about this? So with the increasing adoption of LLMs in real world applications, you should consider the security and safety of the models. I think, for instance, we've seen that LLMs have been integrated into various industries. For For example, in finance, you find that people use them for sentiment analysis on financial data. I think one good example would be the Bloomberg GPT. And if an attacker can design an adversarial suffix that can change the model's prediction from positive to negative or negative to positive, then clearly this would have a significant effect on financial decisions from some people, and this could have an overall effect in the stock market. I think when it comes to security, you just need an attacker who is motivated enough to cause chaos, and with no time, they can explore these kinds of vulnerabilities that are already known. Then the other thing about adversarial attacks is that researchers have shown that they are transferable. So when someone finds an attack that is effective, for example, on an open source model that is performs a white box attack, this attack can be used and can be transferred to other closed source models, and they are quite effective. I believe in the references you'll see in one of the papers that they've shown how simply designed adversarial attacks are quite effective even on models where they did not have access to the model's architecture. Then, with the knowledge that the attacks can be transferable to other models, I think it is quite wise for us to care about how our models can be more robust and how we can improve their performance against adversarial examples. So this talk would not be complete without talking about defenses and how you can protect your model from this known vulnerability. So one of the ways and one of the most effective ways you can use to protect your model from adversarial attacks is to always sanitize input from users. Don't trust user input, and do checks to ensure that input that the user provides you conforms to what your model can handle. So for example, as we've seen in the initial example, that someone can just the input might not have perceptive, like you cannot see the adversarial, that is an adversarial example, but if you sanitize the input and ensure that it conforms to what your model can handle and what you've designed your model to handle, then you're able to weed out that attack even before it's processed by your model. So you can also explore paraphrasing the inputs through which but this should be used in conjunction with other methods because it might not be as effective. And it is also important to note that paraphrasing could result in model performance degradation because your model might not perform as it would have with the initial input that the user gave. Then the other effective way to defend your model against adversarial attacks is adversarial training. So this involves training the model with adversarial examples, and this enables the model to generalize well. Even when it's given an adversarial example, it's still able to make a correct prediction because you've trained it. It's already seen this kind of data before. So it's able to give a correct prediction, and it's not fooled as easily as having not seen any adversarial examples. Yeah, so you will use the adversarial examples as part of your training this data set. One, I think, key thing we should note about adversarial training is that this could be quite expensive because it requires high computational power to generate the adversarial examples. So yeah, we've seen that adversarial attacks are carefully designed perturbations added to inputs that trick neural networks into producing incorrect input. So LLMs are vulnerable to these attacks, and attackers can design an attack that is also effective on other models. While deploying your models, you should be wary of potential attacks and use defenses such as sanitizing user input and adversarial training to make your models more robust. So I think one of the main thing you should care about here is that one, that adversarial attacks are transferable to other models. So this should be something you should be, even while using open source models and while leveraging other LLMs out there and integrating them in your system, you should be wary that attacks on basically attacks designed for other models could be used to exploit your model. So you should probably implement one of the defense mechanisms we've talked about. So with that being said, I hope you've learned something from this talk, or at least it piqued your interest in security in machine learning. And yeah, you can go through the papers in the further reading section and to get a good grasp of how the attacks are implemented, and also just to find out what other researchers have been up to in the field of adversarial attacks. Yeah, so thank you for your attention and time, and feel free to reach out to me on LinkedIn to talk about ML, accessibility, and software engineering in general. Please let me know if you have any questions. Yes, so I
Bernice.
think I have some questions.
Yeah.
Oh, yeah.
Thank you so much. I think there are a couple of comments in the chat that maybe you have a moment to
Sure.
read.
Yeah, I think we have time. So I see.
I'll just show
Would
this
you
first comment.
say?
Yeah.
Okay.
Is it showing up on stage? No, it's not. So the first one was, can you see it there in the chat?
Maybe you could just read it out so that we are
okay,
aligned.
Great, sure.
Yes.
Yeah, so I'm from Sujit. He asks, you will probably be covering this, but looking forward to learning about how to compute the adversarial perturbation to do this. Was that something that was
Yes,
covered?
so I think, yes, we've covered how the gradient descent, how we leverage a gradient descent to define. I think I'll just go back to. Okay. Yes, but we've covered this, and I can give a more detailed explanation, I think, afterwards if he doesn't feel we've properly covered this.
Great, thank you. So I'm not seeing any response, but sounds like you've covered it. So that's I hope Suji got his answer. So there you go. He said you did cover this to some extent, but it seems like it would work only in the binary case. Does that make sense? By setting the features to increase the gradient. So thank you. That's his response.
Okay. I think Sujit, I think I'd suggest one going through in the further. I've shared the slides and to this. So if you go through one of the papers here, you'll find different researchers will use different approaches, but the underlying idea is that we'll try to increase the loss as compared to when training, where we're usually trying to decrease the loss function. When trying to design an adversarial example, we are trying to increase that loss function, but to a certain degree, not completely that we go off the mark such that someone can see that clearly this is different, this input is different from what you'd expect. Yeah, so I think I'd implore Sujit to go through one of this. And also, I think, I see he mentions that he'll go through he's looking forward to the papers. So yeah, he can get more info there, hopefully. And also you can reach out to me and we can have a talk about this more.
Excellent. Thanks, Bernice. And I think there's just one more there. Are there any open source tools to monitor or prevent the adversarial attacks?
So I think so far what I've seen are mostly tools to generate adversarial attacks. Actually, I have not seen tools to prevent or monitor. Yeah.
Okay.
But I'd be happy to look into that as well. I think, but I haven't seen any tools to prevent. Yeah.
Great, thank you. Now we have a question in the Q&A. There we go. So, in your experience, would you say that neural networks are more, less, or equally prone to such attacks compared to classical ML algorithms, such as logistic regression, decision trees, etc.?
So I think I would say neural networks are more prone to adversarial attacks, mainly because it's easy to leverage the whole gradient descent idea, right? But for logistic the simplicity of logistic regression or basically traditional ML algorithms makes them less prone to this. But it doesn't mean they don't face this problem. They also, like, I think you could also generate adversarial examples that would trick classical ML algorithms. So I think I can answer that. I can also add a comment later on to Nishan. Yeah.
Great. Thank you so much. All right. Are there any more questions from folks? I think that's, there's another. So this one here, I don't know if the comments, they're not. It's not a question, but for training LLMs using contrastive learning, sentence transformers, uses something called hard negative mining, which is a good example of this. So that's just someone sharing some insight there.
Yeah. Yeah, it's Sujit. Thank you, Sujit.